to. It's a pleasure to have you back here, where we get to share, learn, and grow together. So I'm just going to request one participant to just unmute, say hi to us, and let us know your day was before we dive into what we have today. So yeah, although we've not shared the video, just anyone to unmute, let us know how your day was, and yeah, we begin. Waiting.
Hello.
Hello.
Yeah, hello. Good evening.
Good evening, Engineer Rashid.
Yes, hi. How are you? Good.
I'm good.
Okay. So it's going well. Everything going perfectly fine, and we are growing ourselves into Revit structure, and I really like it. And there is no problem right now. We are enjoying.
All right, Engineer Rashid, thank you so much.
Thank you.
I guess in that spirit, it would be really not the best idea to have a gentleman and we fail to get a lady to say hi. So any lady that can unmute and say hello, then we'll begin. Ladies. I see we have very many ladies. Anyone to unmute and let us know, to represent the ladies before we begin. Okay, all right. I'll assume everyone is fine. So allow me share my screen. Sorry about that. I think it was my network. I lost you a bit. Sorry about that. So I will share my screen again. I hope my screen is visible. Just type a 1. Am I audible? All right. Thank you so much. I'm going to open a drawing. There's a drawing, I think, from DeepTube 1. Engineer Omar Fabius had some amazing work. So it's the drawing I'm going to work with today. Yeah, okay, my screen is visible. So what we are going to model today, we shall model the slabs. We have a solid slab for the first floor. It also has ribbed sections. We have a ground floor slab that is also, we shall portion it into the different layers. That will be at a later stage. We are going to work on the different foundations we have, the combined, the isolated footings. Then work on the foundation walls and their strip foundations too. So, and the staircase. So get ready. All right, so to begin with, we are going to begin with the ground floor. I'm going to open the ground floor slab. So along the ground floor, we have a solid slab that runs around the entire columns. It occupies all the entire columns. We are going to model it. Then we shall model cause. Let me just take you to. Let me open. Let me open a PDF that we are working with. This is the PDF we are working with. So we shall model this. This is a ribbed slab. It has ribs in these particular sections, and then these other sections are solid slabs. Then we have a ground floor slab. It is visible in this section. This is the ground floor slab that we are going to model. Yes, so let me open my Revit again. It is freezing a bit. Sorry about that. I don't know why it is freezing. Let me pull this one down and I share again. All right, I hope my screen is visible. Is it? You can just type a one. All right. So this is the ground floor. We are going to model an entire solid slab around at the level of our top of foundation. So I think by now you must be getting used to the workflow. We model most elements using the structures tab. Of course, today we shall model one element that is that will fall under the architecture tab. All right, so structures tab, you go to the floors. We are going to model a structure floor. As usual, you might not find what you need here, but we shall begin with the generic 300 millimeter thick. It's what we are going to edit. So I'll go to edit type, and as usual, I will duplicate and name it the ground floor slab. You can go ahead and be specific if you're sure of the thickness. So I can call it a 300 millimeter ground floor slab. Okay. The thickness is 300, so I'll just hit OK. So Revit will open. Revit will open the modify or create flow boundary. It will update all these ribbons to coincide with what you're trying to model. We've used most of these, the copy, the move. So the panel that we are going to be using is this one. There are very many ways of modeling a slab. You can pick lines. You can just use a rectangle. This is the easiest. So I can just snap to, for example, if I want my ground floor slab to pass here, so I can just snap to the intersection of that. Then I pull and snap to another intersection of the grids. So you can see it has drawn the boundary. So we specify the boundary and Revit will model the slab. So when I accept, you will receive this notification. The walls that go up to this floor will attach. So you just accept so that they attach. Now, this is the, you might not view it, so I'll just turn it into shaded so that it is visible. But as you can see, the columns are still out. You can go ahead and modify this, but we can use another method of creating, just to show you another method. So I can just delete this. I'll repeat the same procedure, structure, then floors, but we have already created the ground floor slab, so it's what I'll select. Now, instead of just using a rectangle, I can use pick lines. Because it is these columns that were out, I can assume that I want my slab to extend beyond the extents of the column by 500 on either side. So using the pick lines, I will specify the offset that I want my slab to be at 500 millimeters from the extent of the column. I will accept. Then pick lines, it depends on how you approach. For example, if I approach this, you can see the dotted line, this one that is somewhere here. So when I approach it from this side, you can see to offset this line tones. When I approach the same from this side, so the same applies to here. If I want this edge to be offset up, I'll approach it from down so that it offsets. Then this will act as my boundary. I'll repeat the same because now I can have a straight line this side, so I just need another line this side. I will offset that to act as my boundary. Then I will also offset this. I will approach it from this side. I offset it. Then I will offset this one. So and now I have 4 lines that can demarcate the extents of my slab. So I'll use the trim extent corner because then I can join different lines. So all I have to do is select the first line and select the next, and Revit will join for me. So I'll also choose this and select the line that I drew this side, and Revit, it continues to draw the boundary. So I'll select this and select this line. It draws, then I select my first line, select my next. We have the same boundary that we had earlier, but now with extents that match what we need. So I will just accept, then click on the attach because I want everything to be attached. So we have a solid slab in 3D. This is what we have just created at the ground floor. This is the slab we've created. So now I think that is clear. There are very many options you can use to create a slab. So I'm going to move to the first floor. I will open the PDF. So this is what we are going to model. There's a side slab that runs around every floor. It has ribbed slabs here and so on. So we are going to model this slab. I'm going to model it on the first floor, but it will go on other floors after we've fully edited it. So this is this marks the demarcation of the slab we are going to model. It will come curving like this, curving, following the extents. And where we have the cantilever slabs, it will also follow the same, enclosing the entire structure. So on the first floor, you remember the same procedure. We are going to repeat the same procedure that we used earlier on. When you go to structure, floors, but now we are not going to use the 300mm ground floor slab. I'm going to edit it. We are going to use a slab that is 175mm thick. So I will edit this, duplicate it, then this is going to be a 175mm thick solid slab, floor slab. So I can maintain this solid floor slab. And I accept. But now, since we've changed the thickness to 175, I'm going to change this to, I'll just cancel. So to change the thickness, you just come to the construction parameter here. You go on the value, there is edit. So you click on edit and come and edit the thickness to 175. Apply. Okay. Now, when we go to the families, you will realize now we have a 175 millimeter thick floor slab. It's the same concept that we used earlier on. You can't, for example, for this case, you can't use pick lines because you have to pick every line at the boundary because this is how the slab is going to move. You would consume a lot of time picking every line. You also can't use the rectangle because for it is a defined shape, but here we have very many curves, very many lines and so on. So it's the pick lines that is now the best for this. So you don't need an offset because we want this same slab to follow the extents of the beam like this. So you just leave the extents as 0. Ensure we are in the family that you have created now. It's the same concept like we picked lines and join. We are going to pick lines along, just lines where there is a change in direction. For example, I'll pick this. I'll pick this line, pick this. Then later on, Revit will join this. I'll pick this line and this line, Revit will join for me here. I'll pick this line and pick this line. Then Revit will join. So that is what we are going to do. So I'm going to pick lines along the extents of the beam. So when you hover near here, you can pick this line, the extents. Remember, we are picking wherever there is a change in direction. So here, there will be a change in direction. I'll pick this line. Because there's a change in direction, I'll pick that line. The same applies here. I'll pick this line. If your slab goes like this, then you pick this line. If you decide to take it like this, then you have to pick this line. Pick this one. Wherever there is a change in direction, you pick the line. Now we've picked this line. For this arc of our cantilever, just make sure you pick, for example, you can zoom in and pick a line that is straight that connects to the curve. Make sure you also pick the curve and pick the extra entity that completes this entire curve. So I'll pick this line. Remember, we are picking wherever there is a change in direction. So I've picked this line. I will pick here. Wherever there is a change in direction, I'll pick that. Pick this. I will pick this. Pick this. Now I don't, okay, here there's a change in direction. We picked this line, so I'll pick this, then pick this. Remember here you have to pick all the lines that form this, that curve. So I'll pick this line. There's a change in direction, I'll pick this. So you just go on picking lines. Where there's a curve, make sure you pick everything. So I'll pick this line. There's a change in direction, pick this. Pick this, pick that. Change in direction, pick that, and pick that. Pick this. There's a change in direction, cantilever. Pick all the elements that form this curve. There is a change in direction. I'll pick that. Now, because I picked this, it will be extended over here. I don't need to pick any other line here. I just need to pick where there's a change in direction. I hope I picked the right entity. I've picked a wrong entity, but we shall see how Revit deals with this. So there's a change in direction. We would have deleted it, but we can see Revit will be intelligent enough to highlight it. So I will pick this where there's a change in direction. Remember, if you have very many entities that are in one place, you can use the tab. You just position your mouse and then place the tab. It will hover through all the available entities until you select what you want to select. So I will pick this, pick that. This is where we started from. Yeah, so it is better you move in one direction. For example, you saw we went the clockwise direction. Let me turn into wireframe so that the lines are much visible. So this is what we have. Now we have drawn lines wherever there is a change in direction. All we have to do now is to use the trim extent corner. So trim extent corner, as we did earlier, all you have to do, move in a defined path. You can move clockwise or any direction, but you should be in a manner that you're able to tell where you're heading to and where you're done. So all you have to do is pick the first line, because now there's a line here, there's a line here. Revit will join these two very well. So just pick the next entry. As you can see, Revit just connects. So pick first line, second line, and Revit will join for you. So there's a change in direction, pick this line, and Revit will join this one. So pick this and pick this, Revit will join. So pick that and that, pick this and this, Revit will automatically join. So I'll pick this and pick this line. Remember here we picked all the entities, so I'll just pick that and pick that, then pick this and this. This is my line. I need it to join with this one, so it will join, pick that and that, pick that and that, pick this and this. So at the end, we are going to skip a line so that we see how Revit will treat that. It will be intelligent enough to know that you skipped a line and it will notify you. So this is our line. I want it to be joined with this one. Revit will join this one and that one, this and this. So let us keep this corner just to assume, because it happens, you will skip an entity. We shall see how Revit will treat that. So I'll join this to this, then first, second, your first and second, your first and second, your first and second, then this and that. So this and that. Remember here we have another entity we drew unknowingly. We shall see how Revit also treats that. So I'll join that to that. Move in a manner that is continuous. Your first line, second line. Your first line and second line. Your first line and second line, then. So remember the lines we skipped, we shall see how Revit does that. So first line, second line, and then this line and this line, then this line and this line. So literally we are done joining. So we are going to see what happens in case you've skipped. So I will accept. You get this notification. Don't quit. When you quit, you will have to redo. So you can see it highlights where you have entities. For example, this line, it can't clearly identify which path to take. So just click on continue. This line, we don't want it, so I will just select it and delete it. So let us hit enter again. Remember, there is a portion we skipped also. It will still notify you, then you click on show, it will show you the entities that you skipped. So don't click quit, just continue. Launch again the trim extent corner, join this to this, and just accept. So it will still ask you because you have other entities. So just say attach. Remember, we had earlier turned it to wireframe, so I'll turn it back to shaded. And this is the slab you have that is 175 millimeters thick. So this is what we have modeled so far. Just a hint, don't click quit. When you receive a notification, just click on show. Revit will highlight for you the entities probably that you have missed or extra entities that you have. So don't just click on quit, just click on show, it will highlight. This is the side slab. You can see these are the different cantilevers and their shapes. All right, so I'm now going to move on to modeling the different foundations. We have the combined. Still, you realize we shall build on the principle of peak lines when we are doing some of them. Unless someone has a question in regard to this, I don't expect a question on the ribbed slabs, because yes, we shall model them. Yes, we shall model them, but after we are done. So we shall model them later on. Don't worry. Don't worry. So, all right, so I'm going to proceed now. I will just open the PDF again. So what we are going to model are these ones, the different footings we have, the different, let me just, this is what we are going to model at the top of foundation level. So we are going to model these footings. They are different dimensions, the combined ones. You realize the combined ones, we are going to still use the peak lines aspect. Yeah, and these others are way easier. So why the top of foundation? You remember the 3D we have, so I can just go to the front. So this is the structure engineer Omara model. So we are going to attach footings wherever we have different columns depending on their dimensions. So at this level, the top of foundation level. So that is why I'm opening the top of foundation level so that we model everything on the top of foundation. So I will just go back to this so that we note, I'm going to note down the different foundations we have. It depends on how you want it. I prefer noting all the foundations, the different types, then we model at once. So for example, footing 2 is 1800 by 1800 by 450. There's footing 3 that is 2.6 by 2.6 by 0.6 meters, and there's footing 4 that is 3,200 by 3,200 by 750 millimeters. I think when you try to look at this structure, it has a symmetry somewhere. So we have these columns as footing 2, they are similar. Then we have these ones as our footing 3. Then these ones are similar. Then we have the combined footing. So this is what we are going to model. I will go back to my Revit. Remember, we are on the top of foundation. So this column has a footing 2 that is 1.8 by 1.8 by 450 thick. The same applies to this and this. This one has a different footing, and we can begin with these ones. Now, to model the different footings, still you go to the structures. You can see in the foundations where you have isolated these ones. There are also slabs and wall foundations. So we shall choose the isolated. By default, of course, Revit comes with different families. As the idea is always we duplicate the family that is existing to match what we want. So I will edit type, duplicate, and then label it. So we have a footing 2 that is 1,800 by 1,800 by 450 millimeters. And then, but we have now to adjust the dimensions to match what we have referred to. So I'll just change it because this one was already 450, then apply and accept. So you can see, because it's the footing we have, you can see it over your cursor. Now you can be able to place it anywhere. Because this is an intersection of grid, you can just click and you have a foundation, a footing placed. When you go to 3D, it is right here. I will just rotate this, and so this is what we have placed. But now there's a quicker way, because this is a big structure. There's a quicker way. The moment you go to structures, isolated footings, and you choose the footing you want. For example, we know all these columns are. Let me first, I'm going to just delete this, then I showed something. So isolated footings, this is footing 2. When you come to, you can be able to place columns at grids or at columns. This is automated. So for example, if I say at grids, I can just highlight the grids. Then Revit will model footings at every intersection of grids. But as you can see, this is not accurate, does not represent what we need. It can work on a small structure that has very few grids, and you have columns that are on every grid intersection. The other one is to place at columns. So now, because I know different columns have different footings, I don't need to select the entire structure, because of course, when you select the entire structure, it will create for you columns on every. So now I can be able to choose at columns, then I choose specifically those columns that I know have footing 2. And then I accept. Now, the beauty with this is that you don't need to zoom in and make sure the footing has been placed at the center, probably where you don't have grid intersections. So Revit does it faster. We can go back and you can see all the columns have been given the footings at their centroid. So that is a faster way, because these footings are the same as this one, so we can repeat the same process and model these ones. Of course, we are going to reach other combined footings. I will show you the other way. So still structures, isolated footings, but now remember we created one, we shall create others. So I can use the same principle. I say at columns, then I highlight all the columns that need footing 2, then accept. And we are done. So that is footing 2, meaning we have modeled, oh, sorry. We have modeled all these ones at the top, and these ones, I'm sure you have an updated drawing. This footing is at the centroid of the column, so don't worry about this location. So now we are going to move on to footing 3, that is 2.6 by 2.6 by 600. We place it at this column, this column, and this one. So I will go back to Revit. Structures, footings, okay, I will just save. It has hinted to save. Footings, now we are going to edit the current type we have to match the footing 3. Duplicate, then I'm going to call this footing 3. It is 2.6, so 2600, and it has a thickness of 600. Remember, when you click OK, you need to adjust the dimensions to match what you currently have. So I'll just highlight this. I'm just holding down my mouse key. So 600, 2.6, and 2.6. I don't know if someone is trying to communicate. So we have created a family of footing 3. So let us also create the family of footing 4 so that we work faster. So I'm going again to duplicate this and call it footing 4. That is 3.2 by 3.2 by 750. And press OK. So you edit the dimensions. It is 750 millimeters thick. It is a 3.2 and 3.2. Apply. Okay, so this is what we have created. It is a 3.2 by 3.2 by 0.75. As you can see, it's already on one. Footing 4. It's this one. So let me move in order. Let me go back to footing 3 so that we can place them along these columns. Now to place them, you can zoom in, and because this is an intersection of grids, and just snap. Or you can go to columns, then I'll select that. I'll hold down the control. I select that. I hold down the control. I've held down the control button and then just accept. All footing 3 columns have been modeled. I will go to footing 4. So let us just check the PDF to confirm where we have footing 4. So this is footing 4, footing 4, footing 4. Then these two are also footing 4. So we are going to put footing 4, this column, this one, and these 3 columns. Okay. All right. So make sure you have your family set as footing 4. We have exploited different methods. You can zoom in and snap at the center, or you can let Revit snap for you at the center. So I will just launch at columns, select those, hold down the Control key so that I can select other multiple columns. So these are the columns, and I will accept. Okay, accept. I will just, these ones are intersecting. Let us just find out why. Okay, this column is positioned at the face, and this one is positioned at the face because we have a staircase here. I think probably that is what Engineer Omara forgot, because this column must be at the face, otherwise it is going to enter into the staircase. So to just confirm that, I'm going to, let me first turn it to wireframe. I'm going to move this to the top of foundation. I hope this is joining the highlighted wall. Oh, okay, I will just cancel, then do it again, and apply. Okay. It has a hint on, but all we are going to do, I will just turn this into, I want to move this to flush with, it flushes with a beam or the wall that is 200. Sorry about that. So we want this column to flush with a wall that is 200. On the top of foundation now, the easiest way to do this, I can create a beam that is 200 so that it demarcates the wall. Then we just move it from that point. So let me just delete this. Then I'm just creating a wall. It is 200. I'm just creating a wall to use it. Then I will delete it. To use it to position these columns very well, then I will delete it. But now to do this, moving them at this level, the top of foundation, Engineer Omala, you will have to do it at all levels, because this is going to just move only the it is going to just shift these columns at the top of foundation level. So you have to adjust this. I know you adjusted this, so you have to adjust this on the every level. So I'm going to just select the column and I launch the move command. So I'm going to move it from here and it fetches with that. So I'm going to do the same this side. But please note, you have to adjust your columns at all levels. So I'm going to delete this that was demarcating the, so now we can press back the columns again. As we said, structure isolated footings, then now I can use the at columns, then I select these and apply. Okay, so we can go to the 3D and yeah, you can keep checking the 3D to motivate you, but yeah, that is what we have achieved so far. So I'm going to go back to the top of foundation. Now it's time to model the combined footings. Now how Revit models the combined footings, they are modeled as slabs. So we are going to model so the combined footings are modeled as slabs. So literally what we are going to do, we are going to model a slab that is going to enclose the extent of our 4 columns and these 4 columns. So I'll go back to this one is a 3.28 by 638 by 850. It's a combined footing. So we can begin with this one because it has 2 columns. It is much faster. So let us begin with. I'm going to just go to its detail to understand exactly how the column is placed. So as you can see, this is 1350. And also this side is 1350, the column is 500. So the column is 1.35 from the edge of the slab. The same applies to this side, 1.35. Also note, it is 1.315. This face is 1.315 from the furthest side of the combined footing, which is different from this side. Okay, this side maintains a 1375. I'll just confirm. Okay, no, it's still different because the columns are different. So let us begin with this side. It is 1315 from this face and it is 1350 from this face. You remember the pick lines command that we use. So I'm going to go to Revit and pick this face of the column, offset it by a distance 1315. Pick this face, offset it by a distance 1350. Repeat the same this side. This face 1350, this face 1315. So that we now have this boundary. Okay, so let us begin with the 1315, then we'll go to 1350. Someone is drawing on the screen. I'll take as a motivation. So we said this face is offset by 1315. and this face is offset by 1350. So to do that, remember structures, but now we are going to use the slabs because the combined footings are modeled as slabs. I can begin by duplicating it, or you can do it after, but I will begin by duplicating this. I'm going to give it a name. This is, let me just, I think this is footing 2, okay. So this is going to be footing 2, okay, combined footing 2. Combined footing 2, the dimensions it's 3280 by, you can input the dimensions here or you can leave them because we are just inputting them. Edwin Juko, Engineer Edwin Juko, you are writing on the screen. So this is the combined footing 2. It's a slab. It's 850 millimeters thick, so don't forget to edit its thickness to 850. Don't forget to edit the thickness. So I'll apply and okay. So it's the one we are working in. So whatever we are going to edit will match. So I'll use the pick lines and then offset this side by 1350. Remember what we said, how you approach the line matters. I will just delete this. So how you approach the side matters. We are working with an offset of 1350. I'll press enter on this side. So when I approach it from this side, you can see the dotted line somewhere here. That is the 1350. So also this side by 1350. But this side is offset by a 1315. We can just go back and confirm. 1315. So I will approach this side and offset it by, I will adjust this to match 1315, then press enter, and then approach it from the upper part so that it can be drawn. We can move to this column because now we have a line here, we have a line here, Revit will join, but we need another line here. So I will go back. We just need this offset, then we shall be done, which is 1290. So I'm going to go back. I'm still in the command. Pick lines, I will give this the offset that is 1290, then press enter. I'll come back and approach this line from down so that it offsets at this location. When I'm done, now I can use the trim extend to corner. So all I have is to pick this line and that, Revit will join, pick this and this, then this and this. And we have combined footing. So we can just go back to the 3D just to see what we have, and there it is. Now, the others are going to be much easier if we've done this. So we are going to go and explore this from the PDF. This is what we have. Please, we can, I'm going to note down this because now what is critical here is the offset of this face of this column to this, which is 325. I'm going to note it down. It is 325. So this is 325 and also 325. So it's the same dimension. This face I'll offset it by 325, even this by 325. But now the beauty with this, when I do one side, because now when I offset this by 325, I would have created this line. When I offset this, I would have created this line. Meaning this line is covered and this, all I have is to have other two lines here. So as you can see here, this one is offset by 325. This face is offset by 325 and this is offset by 275. Okay. I'm going to just note those values down. 275 and 325. This 325 is the same as we have here. So we just have 325 offset, then a 275. This face was offset by 275. So those are the lines I'm going to replicate in Revit. So when I come here, this is offset, this face is offset by 325, 325. This face is offset by 275, and this is offset by 325, and we shall be done. So same structure, slab. Then let us duplicate this because we are dealing with a 4.1 by 4.4 by 850. So I'll come to this, I will duplicate it, rename it into, I'll give it footing 3. I hope it is footing, oh, it is our footing 1. Okay, the combined footing 1. It is 4.1 by 4.4 by, let me just confirm, by 850. 850. Okay, then don't forget to add to the thickness, but we shall leave it as 850 because it is 850. Then apply. So combined footing 1, it's what I'm going to draft. So I will go to the peak lines. Remember, this is offset by 325 and this by 325. So I will go to my offsets and punch in the 325, accept. I will approach it from this side. The side you approach it from matters. When you approach it from this side, it is going to go this side. So I'll approach it from here, approach this one from here. So we have lines here. So all we need is this side. I will just confirm 275, 325. So with 325 still, I can offset this face. Then I need a 275. So I will adjust this to 275, hit enter, then I offset this. Now with these lines, we can be able to now launch the trim extent cone. So first line, second line, first line, second line. You have a combined footing. Okay, so we can, this is what we have. So we are going to do this one faster, then we shall be done. Okay. So I'll go back to the PDF so that we don't need to go back to the PDF because it's the same footing one. So we just need to replicate it onto this. So just to confirm, I can have, I'm going to just put dimensions here. Okay, 3.2. I think engineer just missed something small because when doing the dimensions, because as you can see, this is a 3.4 and 2.2 and 1, that is a 3.2. So engineer has a 3205. That is something small. So now we need a footing that is 4.1 and 4.4 this side. So if we already have these dimensions, for example, if this is a 3.4 and I need this to be a 4.4, so this would mean a 3.4 minus 4.4, which would be 1 meter as balance. So divided on either sides, meaning I would have a 500, but from the grid line. 500, 500. Now it depends on the column. When I hover over this, it is a 400 by 400. So if it is a 400 by 400, meaning this is 200 up to here. So if this is 200 from the 0.5, meaning I have to offset this side by just 300, and I'll have where the footing will pass. So I can do the same for this side because this is a 3.2, and I want the entire width of this to be 4.1. So I will just leave it at 3.2. So 3.2 minus a 4.1, you'll get 900 millimeters. Divide by 2, meaning I have 450 extra, 450 extra. Now it depends on the column. This column is 300, meaning it extends by 150, 150 on either side. So if I need an extra 450 minus the 150, I'll have to offset this by 300 in order to achieve the 450 that I want to offset. This is how you work out this. So I'm going to do it concurrently so that, so I'll just go to, and yeah, we are in footing 1. So this is it. This side should be 4.4 minus a 3.4, that is 1 meter. Meaning on either sides, I should have an extension of 500, 500 to have the 4.4. But this column is 400 by 400, meaning I just need an extension of 0.3 and I'm done in simple terms. So I can just launch and offset it by 300 that I need to achieve the 500 and make it a 4.4. So now if I have this, I just need an extra line this side. So 3.2 because I want this entire width to be 4.1. It's a 4.1. So if I want it to be a 4.1 minus the 3.2, I'll have that as 900. But it is on either sides, meaning I need a 450, 450. We saw this column is 300 by 300, meaning from here to here, that is 150. So I need this extra, the one from 150 to make 450, which is 300. So I need to offset this side by 300. Okay, I approached it from the wrong side. I'll just click escape. Oh, sorry. I can use this, then delete. I also delete this line. So we have this offset at 300, meaning I can join this. I can be able to. So I've gotten this other side. Now, all I need is to work on this column and I'll be done. Remember, this is 500. We need an extension of 500, an extension of 500. But these columns are 300 by 300. In simple terms, we have a 150 covering, but we need 500. I'll just confirm these columns, their dimensions. Oh, I will have to, so let us just note, because I'm going to, I need this column, and I'm going to first cancel so that we get the actual dimensions of the column engineer used. So remember, we have offset this by 300 and 300. Okay, so I'm going to just cancel so that we confirm the dimensions of these columns. So it is 300 by 300. So if engineer used 300 by 300 and we need to achieve a 0.5, so I will have to subtract a 150. So meaning I have to offset this by 350, this side by 350. And this, so I'm going to note down the 350 millimeters that I need to offset on this downside. And this, we need an extension of 450, but this one is 150 because the column is 300 by 300. So 450 minus 150, we just need to extend by 300 and we shall have a 400. So in simple terms, this side we offset by 300, this side we offset by 350. So I'll go back to, okay, I will save structures. Okay, we are already in the command. So I'm going to go back to the peak lines. Remember, we offset this by 300. So we are going to pick lines. We are going to offset this by 300. I will punch in 300, enter. Then we bring back our line. Then again, we offset this by 300. We bring back our line. But remember, the 450 minus 150, we need to offset this by 300. So I'll offset that by 300. Here we need 350. So I will adjust this to 350, hit enter, then there you go. So we can now just launch the trim extend to corner. First line, second line, first line, second line. Apply. And we have a combined footing. So you can just view the footings you have created. That is it. So for the lift core, it is 3.4 by 3.4, so you can be able to offset. You know the dimension of the lift core. What extra dimension do you need to achieve the 3.4? Divide on either sides, then offset the edge by that distance, the edge, then join and create a combined footing for the lift core. I'm going to ask if anyone has a question in regard to what we have covered for now before I go into the foundation walls that are going to be very straightforward. Take note of the combined footing. You're going to exploit the same principle we used on the solid slabs on different floors. So you'll be working with the peak lines and the dimensions. You will manipulate these depending on the PDF that you have and know how much to offset. So unless someone has a question in regard to footings, I'm going to move forward. Hello.
I'm Daniel.
Yes, Engineer Daniel.
I was asking, just, okay, a side note on this. I was asking about to get the sizing of the, let's say, for the foundations and all that. You have to do analysis in a different software, or can this one do the same, or you have to, or you can use this for preliminary the sizing of the foundations, then you do the analysis on another program? Or how do you come up with the foundation sizes?
All right, Engineer Daniel.
Yes.
The question you've asked will be covered in the analysis of reinforced concrete structures, but just a small hint. Depending on the columns you have, for example, this column, it carries a certain, this column here carries a certain weight depending on the nearby columns and the load transfer system from the slab to the beams. Now, all these columns carry a certain area. That area will be transferred into the different loads carried by these columns. Now you go on and now group the columns. You group them in such a way that, for example, these ones will have the weight they are transferring to the soil that is within a certain range. These ones will have a certain range, and these ones, all of them will have a certain range, but you group them in order not to have maybe 1,000 different footings. So you group them and analyze the worst possible column that has the biggest load in that group, whether that footing can dissipate the load it is carrying to the foundation safely. Now, if it can, the column that has the biggest load, meaning all other columns are okay, unless ground conditions change that are catered for at the time of excavating these footings. If there is any change, the designer can be able to run the analysis very fast. For example, for this combined footing, if the estimated bearing capacity actually is found to be way above what was earlier, meaning that designer can rerun the sizing of this footing at that particular stage. But the principle is they are grouped depending on the range of the forces they carry to form different groups. Those groups will turn into the different footings. You see, for example, these ones carry, they are the same sizes, and these ones are different because of the loads. When it comes to analysis, Inginagatimo will exploit more. We can export the analytical version of Revit into other softwares like Robot that we can use to model. So analysis will be done. For example, if you do in Robot, Robot communicates very well with Revit. You can easily be able to import your model from Revit to Robot. But yes, that is basically on the sizing. It is the loads, the bearing capacity, and the grouping of the different columns. Otherwise, when we leave them the way they are, you would end up with maybe 30 different footings.
Okay, so that means, okay, usually on site, you will have the bearing capacity known to be able to work out the sizing and all that, basically.
In most cases, what is done, for example, on a plot of land that will take up this entire structure, you might not be able to do individual tests at every point, but they choose points that will represent the overall footings, and they have a range. But usually, for example, when you excavate now, you have better understanding of the actual point where your footing is and its bearing capacity. If there is any change, the structure engineer can easily rerun the foundation, and for maybe if you want the economics and probably the bearing capacity is way better than what you had imagined. So there can be resizing at that actual time if it is needed.
Okay, so, okay. Okay, another question was on the slabs. No,
Yes.
okay, on the foundation steel, I think I'll ask the two questions at once so that I get the answers. Okay, on the foundation, basically, let's say the bearing capacity that was thought to be existing on the site has changed or has differed. Either it has lowered or let's say it has lowered, maybe due to maybe there was a high water table and all that. So parameters that essentially affect the bearing capacity, like let's say, is the like you may find the area was built up. After a while, then the bearing capacity changed because when you built up an area, basically you reduce the bearing capacity of the soil because you find that the soil already has it has more it has other structures bearing on it. So is there a way of computing or finding such kind of values? Because mostly you find where it's built up areas, the bearing capacity that let's say the bearing capacity that is given, you will find at most cases it has reduced, maybe due to the vicinity of the structures that are nearby. So you find that the weight that is imposed by the other structures will influence your bearing capacity. So is there a way of making the bearing capacity dynamic so that when the bearing capacity of, you may find the bearing capacity of one corner may not be the same as bearing capacity of the other corner, or the bearing of the center line of the center of the building may not be essentially the same as the bearing capacity of another section of the building. Is there of of inputting those changes of those parameters into the software so that it gives you a more realistic foundation and a more economical and more realistic way of designing a building. And then the other question was on the slabs. For the slabs, let's say you have different types of slabs. You have a flat slab, you have the normal slab, you have a solid slab, you have on different sections of of your building. How do you design for that using Revit? Let's say in one corner you may decide to have even a solid slab of maybe 250. In another section, because of the loading, you may decide to use maybe a hollow slab. In another section, such kind of design. You find most cases you find that if a building is big and they are trying to be economical, you will find that where the loads are not that much, they will usually tend to, or where the loads are very big, they will usually tend to do other types of slabs. Maybe you find a hollow slab or something of that sort. And some sections you may find that the slab are not the same thickness. So is there a way of inputting those different sections or highlighting those different sections, especially maybe on a cantilever slab? You'll find that the thickness of that slab will not be the same as the slab that is a simply supported slab, essentially.
Thank you so much, Engineer Daniel. Yes, for example, these highlighted points along your top of foundations might have varying bearing capacity. Depending on the software you're using, different softwares take in place different parameters. For example, Robot, if you're to model this, Robot will take into consideration several parameters. Actually, it has a soil calculator that will calculate for you the pressure depending on the loads you have, and that is governed by different elements. The soil type you have, the different profiles at that specific point. So yes, it is very possible to vary whatever bearing capacity you have at a different position and reanalyze your foundation. It is very possible. We expected, for example, the question number 2 you have asked. Yes, we thought about it, and that is why we incorporated the ribbed slabs within our model. So yes, it will be covered. We shall show you how you model different. Because, for example, although we have entirely made it solid slab, but we are going to remove out these portions and model them as ribbed slabs. So you have a ribbed slab here, you have a solid slab here of different. It is very possible we shall exploit that worry not. It is very possible in Revit. And we had imagined that to give you great experience. So we have that incorporated and covered. It will be covered, worry not.
Okay. The other question I had forgotten on integration of building with the topo survey. Is there a way the robot can do that, whereby even before designing, you can know let's say like the 0 level, your datum. Then from there you start building up. Is there a way you can incorporate that data? Because mostly you are building on a surface, and it's usually you'll not find it's flat or something. You may find it's maybe slanted on one side, such kind of a thing. Or maybe it's very flat and you need some, because of your mechanical services, most of those mechanical services, especially for the sewer and the stormwater, you will need a bit of a gradient. You will need to create, if your land is flat, you will need to know your, let's say like your zero datum, so that when you are calculating the slopes and the map services, you will have enough slope to allow for the pipe, for the, let's say if it's sewer or the gravity systems, to allow for the water to, or the evacuation of such kind of elements out of the building and into maybe the septic, or into the centralized system. Maybe there's a pipe network or such kind of a thing. So essentially, you will need to know before you are designing. You may need to know, your 0 and how much you are going to how you are going to determine your 0, your datum for maybe it's especially for the maps, the gravity systems in the building.
Yes, Engineer Daniel, thank you so much. If I may ask you a question, have you interfaced with Civil 3D?
Yes, I've interfaced with Civil 3D, but I've done mostly with roads. So I don't know if there is an integration whereby you can integrate your building or the site of the building with with Revit to those to essentially control your, especially the map services, because that's where, especially in buildings, you find that is where the biggest challenge is. You find that maybe during the servicing of the building, it's blocking, such kind of stuff. So you essentially you will need to know, you are grading so that you try to mitigate such kind of a situation, because we had a situation like that in one of the sites. So it brought a big challenge trying to correct that during construction phase.
All right, Engineer. Yes, why I asked Civil 3D, because it has very powerful surface analysis and grading tools. Yes, I understand the building information modeling softwares do have collaboration, but I will hold on to that and answer it later on, probably with extra input, whether we can be able to integrate the super surface modeling tools of Civil 3D within Revit models. So I'll hold on to that. But or I know that Civil 3D has very powerful surface analysis tools. So I will hold on to that, and yeah, I will also. All right, so yeah, that was quite interesting. So we are going to move into foundation walls, and yeah. So I will just, okay. Okay, so let us move into foundation walls. What I've just done is to just shift the file that we have linked onto the top of foundation. So all I did was to select it, and the work plane, you can take it to any level that you want. So it was on the first, I've shifted it to the top of foundation. Now for foundation walls, what is important to note, still we shall be using structures, and they're right here. So the one that is highlighted in blue, that is the foundation wall, but we need to create that wall. Sometimes it can be load bearing. For load bearing walls, it transfers the loads onto the foundation walls. So to model the foundation walls, you need to first have the wall in place. So how do we model the wall? All you need to go is to go to the walls, then wall structure. I'm going to edit the basic wall into, so that it forms our ground floor wall. So I'm going to edit this. We are going to use a wall that is 200 millimeter thick. So I'm going to call this ground. I can just call it the foundation wall, or yeah, foundation wall. So this will depend, you might have it as, so this will depend on the thickness that you have, depending on the, probably the blocks you're using. In Uganda, on simple structures, I always see the normal clay bricks were arranged in the header bond to create this. So I will just accept now. We have its foundation wall. We have a family for foundation wall that is 200 millimeter thick. So what to note, for example, what we are placing is the structure wall. Remember, you can model by height and depth, and we know the difference. The constraint, we are going to constraint it to the ground floor. Okay. I'm going to just escape and confirm. Oh, I'm in the top of foundation. Let us just model and we see the difference, but I'm sure you are aware, for example, structures, walls, foundation walls. So if I leave these the way they are, let me choose center line, we model by height. Then what is important is to snap to the face of the column. So because the wall can't go past the face of the column. So let us just confirm what we have done. So when we go to 3D, it's better I have it highlighted so that we can clearly differentiate it. So I will just zoom in. I don't know if you can, yeah, it's here. So there is a difference between modeling by height and by depth. One models it going down, another one models it going up. So that is the major difference. So on the top of foundation, all you have to do is have your family that you have already set, and then just continue. So structures, walls, then the family that we created, foundation walls. From the face of the column to another face, it can't go. So let me just use wireframe so that I can be able to snap to the faces with ease. Most important to note also the chain. We don't want it to be continuous because we are going to be terminating it at different levels where we have columns. So from the face to the face. So all you have to do is from the face. Okay, this one I'll take it to the middle, then again model from the face. Sorry, I will snap again, model from the face to the face. To see it very well, I will turn on the shaded. So this is basically what we are modeling. You have to model them at every location where you have a wall that is going to go past your foundation, depending on the structure that you have. It can be load bearing or non-load bearing, depending. Don't enter into the column from the face of the column to the other face, because technically that is how it will be. Don't enter into the column. So I'll snap that to the middle, then from the face, and then from the face, so just continue modeling these foundation walls. So I'll choose from the face to another face of the column. Don't enter into the columns, because yes, your walls, your foundation walls don't enter the columns. So model from the face to the other face. Just continue modeling from the face to the other face. Don't enter the columns. So, okay, here I can snap from here. To that, just continue modeling your foundation walls. We have a staircase here, so it will just go and snap to the face. So in 3D, this is basically what we are doing. You're modeling your walls along every wall. Now, what is much easier is the next step. So we expect you to go on connecting every location where you have a wall. So I will just do for a few. So everywhere you have a wall, so I can draw for this. Just make sure you have the right family that you modified, not the height, it is constant to the ground, and we are taking it by the middle. So I can model this to this column, stop at the face, don't enter the face, don't enter the column, because your foundation walls don't enter your columns. So from that to that. Now, what is much faster and simpler are the strip foundations. These ones that we said are highlighted in blue, I will just skip. Those ones that are in blue, they are the easiest to model. So now you can't model them unless you have the foundation walls. You can't model the strip foundations. So all you have to do is go to structures. When you're done modeling all the walls, you go to structures, then you go to the foundation walls. Now you note there are two types. There is one that is bearing footing and retaining footing. This one is usually, it's used for retaining walls and all that. We use the bearing footing, but as it has always been the norm, so when you have the right family, you edit it and give it a name. So I will call it our strip foundation. Just give it a name, but don't forget we need to edit the dimensions. It is depending on what you will be working on. We are going to use a thickness of 200 and 600 millimeters wide. Okay, then apply and okay. Now, when you have the strip foundation, this is the easiest. Because you have the walls, you just click on the walls and Revit will model for you the strip. You just click on the walls and Revit will do the rest of the work for you. This is the fastest thing to model. very fast. So if you have the foundation rules, all you have to do is click. So when you go back in Civil 3D, this is what when you go back to the 3D, you can see these are what we have created. So this sits onto the wall and we are good. So we expect you to model all of them because at the end of the day, we have to produce something that can be executed on site. So to model this, what is most important to model your strip, you must have the foundation walls. Then Revit will model all the other things very fast. So we expect you to connect wherever you have a wall. These walls, wherever you have a wall, you should have a foundation wall and a stripping. The entire drawing. Now, in the next few minutes, I want to cover something I'm going to just cover something small so that we conclude today's. So what we are going to do is the staircase, which is also something nice. So I'm going to move this back to, I can work with the first floor. So I've moved it back to the first floor. So if you're to model, for example, this stair, there are dimensions that Revit needs to capture. Of course, this will also depend on the design you have and what was specified by the architect. So we shall take a trade of 300 and a rise of 150. The trade, that is where you place your foot. So 300 and the riser, that is the difference, which is 150. Now, what is so interesting about a staircase? What is so interesting about a staircase? For example, if we were to model this, remember we are in the first floor. So this is where we have to deviate from the norm because the staircases is in the architecture tab. So when you go to the architecture tab, you will find the saturation zones there. This is where you find the staircase. As usual, we can note you have to, for example, we can just name it staircase 1 because you might have different types of staircases. But what is critical is the riser. So remember, we are going to use 150 and the trade is 300. Minimum run width, that is the span from here to here, we are going to use 1.4. So these ones are usually specified depending on the space you have by the architect. So you will know your run width. So we shall take 1.4. But now what is so important is, for example, apply, okay. Oh, sorry. I will click escape. I forgot to change the nosing. I will just click escape, cancel, yes. So architect stairs, monolithic stair, the one that is cast in place, then we edit the type. I'm going to duplicate and just call it staircase 1. So we are going to change the riser to 150, the tread depth to 300, to 1.4. Now this one is a staircase will move in. It will move, you will have your riser, then a tread. But this riser can be at 90 degrees or slanting. So this is what we are unchecking so that it is not slanted. Then we apply. Now, these options are also very vital because it governs where you're going to place it. For example, this is center. So this is where we are going to start from. If I start from here, you can see my staircase is in the center. So because of this option. So this option, you can turn it and see now it has faced the left where we want it. You can turn it on the right depending. So this is something very fast. Revit models staircases very fast. So you can use these offsets depending on how the staircase is positioned. You can see our land width, which is 1.4, and it is fitting very well. We are going to have an automatic landing. So as you model, you can see 1, 2, 3, 4 down. It keeps counting the risers. So as you model, for example, I will model it the way it is. I snap to 11, so it will model this. Then I will turn and snap here. Now when you turn, the stair also turns. But if I told you turn and it is still facing the different direction, you just come to the offset and change it. So I'll snap it and bring it. You can see it as modeled 10 risers, then snap to this. When you're done, accept. You might receive a warning about the discontinuity in the rails because these ones have to be continuous, but you might have discontinuity. That is very okay. Now you can see our staircase has gone outside of the area. All you have to do with it selected, I can move it. So I can move it from this to bring it back to the region where it is supposed to be. Something small, whatever you've modeled will not appear in the 3D. Why? Because of the visibility graphics there. So
hello, sorry for that. I think we lost Abraham.
hello, hello.
Hello.
Yes, I think I had a network challenge. Let me just finish this. I see Engineer Daniel's hand up. I will take it because this is where we are going to just stop for now. So you might not see the staircase, but it's there. The reason is in the visibility graphics. Visibility graphics control what you see. We were able to see many of these because we were modeling.
Hello, engineer.
I can't see your
Are
screen.
you sharing a screen?
All right. Sorry about that. Is it visible now?
It's loading.
It's visible.
It's visible. Let us just complete something small, then we can. So why whatever we have modeled, it's not visible because of the visibility graphics. So all you have to type just in the model space, you just type VG, then the visibility graphics will pop up. Remember, we've been working in the structures, so you need to toggle on the architecture. You can toggle on others, but you have a lot to select from, so it's better you have the architecture on. So just scroll down to stairs and check them, then apply. And you can see it pops back in your 3D. So we shall continue from here because we shall be able to copy all these onto other floors, model the ribbed slab, and also connect to the stairs. So we expect you to work on the first floor, the ground floor, all the slabs, all the slabs, the footings, the combined footings, the strip, and their walls plus the stair. So, Engineer Daniel, your hand is still up. Probably we can take that and close. Sorry for taking 8 minutes of your time. I had a network challenge and I just wanted to complete something small.
My question was on the foundation wall.
Yes.
On the strip footing itself.
Yes.
I saw it is as if it has captured the top of the footing level instead of the bottom. Ideally it should be when you're doing the blinding for the footing and the strip, they should be on the same level. For me, it looked like you see the strip footing is on the top side, and ideally it should be on the lower side to assist in the moments or carrying the bedding moments. It should be on the lower side. How do you do it to go below?
Oh, it is on
on the top side, and it should be on the bottom. It should be flashing with the bottom side of the footing.
Yeah, I've seen that.
Hello. Hello.
Hello, Engineer Sivanda.
Yes, I get what the engineer is saying, but that is only relevant when you are designing a cantilevered footing. This is a two-footing system, one with isolated bed footings, then you have strip footings for walls. But what he is talking about is it's a cantilevered footing system, where sometimes you have columns that are sitting on eccentrically on bases. So you tie the base of that eccentric column to a more stable base by a beam. So that's when you then need to be careful about the way you position that beam. But otherwise, if it's just a footing for brickwork, as long as it's sitting on firm ground, there is no problem.
Yeah, actually, Engineer Swanda, what you're saying, if at all these were ground beams, they would, yes, be anchored onto these footings. Yes, you're very right. Because these are not necessarily underground beams that are anchored onto the footing. Then if they were anchored onto the footing, yes, you would have them at the same level because you want them to act as your underground beams. But this wall is on top of this strip. So this wall carries your load onto this strip. So that is these are not underground beams that they are tied onto the column, that they have to be at the same elevation down.
Okay, so okay, let's say okay, mostly you find in Kenya when you are doing mostly when you're doing the isolated or the combined footing. In Kenya, mostly we, instead of doing the walls, you will find that they will do the ground beams, then do the covering. So how do you design for that? Instead of the walls, if they are doing the isolated, the isolated footings and the combined, you'll find that they do, they tie that with a grade beam or a let's say a grade beam instead of a strip footing.
If I may get you very well, Engineer, are you meaning a beam here? Because we can also have a beam at this level where we are going to.
I'm saying a beam. You see where the two footings are?
This one?
Yes, where the two footings are. How do you design? Because, okay, like the project I was in, instead of using the strip footing and the wall, we were doing a beam connecting the footing and the footing. You are doing beams instead of a wall. So you do the beams, then you cover the whole thing, then you do your grade beam. You do your not grade. You do your foundations. You do your foundation wall, your foundation slab. On top of it, then you do the ground floor.
Engineer, do you see what is here? Is this what you mean?
Yes, that's
Now,
what I mean. How do you do it? Yes.
On your top of foundation, I've just created a normal beam because engineer already had beams, so I just drew a beam here. Okay. But on your top of foundation. So when you go back to the 3D, this is the beam. But I've tied it to the center of the column, to the center, because it is a ground beam, it would move from the center to the center.
Okay, so for the ground beam, you do column to column, but for the...
You stop at the face of the column because the wall can't...
Hello? Hello?
Hello.
I think he's offline.
Yeah, I think we lost him again. Okay, I think we are past time. Huh? Maybe on the next session, you can start with the questions. and he can explain better.
Yeah.
Because right now we are first time.
The first time, yes.
Yeah, so if you have a question, please, maybe you can preserve for the next session. Before we start the session, maybe you'll get to ask the question, right?
Engineers,
Yeah.
I'm going
Yeah.
to request you with stop here. I think I have a network challenge on my side, but I guess I've covered Engineer Daniel's question.
Yeah, yeah.
Yeah, all right. Have a good night. Sorry about the network disturbance. Sorry. Have a good night. It's always a pleasure to have you here where we get to learn and share ideas. Engineer Daniel, Engineer Salib, thank you so much for your contribution. You've made the session so wonderful. Thank you so much. Have a good night.